So to make it as simple as possible, table formats are standardized ways of organizing data files and its own metadata in an object storage or file system. So in the transition from the data warehouse to the data lake, we lost a lot of control and a lot of guarantees on our data on analytical scenarios. And that's why slowly table format emerged. So the data warehouse offers a lot of control over data schemas. It may offer transactionality, and it offers an easier but limited programming model, which is mostly SQL and its derivatives. On the other end, it doesn't offer much scalability with regard to volume. Another problem of data warehouse is that storage and compute are usually tied together, and they are not fit for non-tabular data. And in the end, also data warehouse were quite costly. So data lakes were a very simple idea. So let's scrap all the data warehouse. We will just split compute and storage in two different parts that can scale independently. And let's just put files inside a file system or an object storage. Let's organize them, and in this way we are very free. But freedom obviously comes at a cost because, well, files are very primitive, so it's hard to update them. It's hard to update them in place. It's hard to enforce schemas, and therefore all the data lakes suffered a lot of problems about data quality, and they were very costly in terms of engineering to keep them organized and functional. So table formats in the end sit on top of data lake technologies and file format technologies, but they offer higher level abstraction with the same scalability of the data lake. So the main idea, as I said earlier, is that we are writing data files with file formats from the lake era, let's say, and alongside we also put a lot of metadata, and we build standard software, let's say, that can be used from any programming language to actually handle this metadata and data accordingly. Okay, this allows a lot of the features that we were missing from the data lake and that we instead had in the data warehouse. The fact that in the end, to build table formats that can actually offer transactionality, we needed to put a database or a locking mechanism in order to access metadata in the proper way. This is in the Iceberg world is called a catalog, and therefore, in order to build a table format, if we are serious about it, in the end, we're also putting in the mix a database. So there are too many. I would love there was only one. So right now, the, let's say, most established are Delta Lake and Iceberg. They are very similar in the concept, but different implementation. Currently, they are both they are open. So one under Linux Foundation, the other one under Apache. But in the end, the main contributors are from Databricks, because Databricks acquired Tabular, which was a company behind Iceberg, which was initially developed at Netflix. And well, another one is Hoodie. Then we have Paimon, which is more recent than the other three. And let's say the new kid on the block, just released a couple of days ago at the end of May. It's Duck Lake. So, in order to explain why Duck Lake is so hot right now, I think we need to go a step back. So, I will briefly talk about each of the other ones, and then it will be clear why Duck Lake emerged. So, Delta and Iceberg, as I said, are really similar. They are composed of data stored as Parquet files and metadata stored as JSON or Avro file or a mix of the two. And the initial idea of both table formats were, okay, let's put metadata alongside data. So metadata is on an object storage. Object storage is a key value fit for objects which are not too small, and each request involves an HTTP request. So when you have to modify the metadata, the only thing you can do on object storage is download the file, modify it, and write a new copy of the file. And this, if you have a lot of transaction, will degrade the latency of your metadata operation with Iceberg and Delta. Hoodie has exactly the same problems. Hoodie is more fit for streaming use cases, has a lot of knobs to configure it and make it faster overall, or offer lower latency than Delta or Iceberg for streaming workloads. But still, all its metadata is on the object storage. Again, this is good for some ways, because you take the object storage, you have everything. You need to access only one place to read the data. Unfortunately, it's not the case for writing data, because when you write data, you want to be sure that your writes are transactional, so that if two clients try to write on the same table conflicting data, one will take over the other and the other one will fail. And in order to do that, in the end, both Iceberg and Delta and UDI put a database in the mix in order to obtain this optimistic locking mechanism. The last one, let's say it's Pymon. Pymon originated from the Apache Flink project, and it's a table format built, let's say, specifically for change data capture use cases. So use cases where you are replicating an operational database and you perform mainly updates by a key. And it internally stores data also using an LSM3, so that this kind of operation are quite efficient. So how does Duck Lake improve the status quo? Actually, Duck Lake improves the status quo because the idea is that let's take an architecture very similar to Iceberg or Delta Lake, but instead of storing metadata inside an object storage, which has all the latency problems that I told you before, let's put the metadata in a regular database. It's not a lot of data, the volume is low, but transactions are much faster and easier to perform on a database. And anyway, on Iceberg and Delta, in the end, you ended up having a database anyway, so why not using it for metadata? This makes Duck Lake very interesting for operations that are performed by many different clients or that write small amounts of data very frequently. But in my honest opinion, there is a big downside, that the database, which is keeping the metadata now, it's a crucial part of your architecture. if metadata scales too much, you will end up with the usual problems of a relational database, which cannot scale horizontally. And again, you have one more piece you need to take care. While when working with Iceberg and Delta, it's true you need a database, but that database has a very small amount of data in it, and it's the kind of data that you can easily recover. While in the case of Duck Lake, that's not the case. And but again, it's beta software. It was released yesterday, literally. So maybe there will be many improvements in the future. I think again, someone talked about the table format war like 1 year ago or so, when when Databricks bought Iceberg or Tabular. Probably there was also Snowflake in the play, and they were probably the first trying to acquire Tabular. So I guess these Duck Lake kind of revamps the table format wars. I think in the end that the war is kind of real, because all these vendors are lurking clients, customers, saying, use our product, but your data will always be free, will always be on an open format, on an object storage. You can leave us tomorrow, and you won't lose any data. You won't spend millions in moving your data from our system to another one. But in the end, I think that's a false dream, because vendors usually invest a lot on a table format, and since they only sell you the engine and not the table format itself, they will build particular features on the table format that can be used only by their engine. This happened a lot with Delta, for example, and I mean, it's legit. This kind of companies need to need to make money, not free software. But I think that's why there's a war. They want you to pick their table format, give you the illusion to be free, but in the end you're probably not, because if you're using to the full extent their platform, which you are paying for, so you want to take the highest return from it, you will end up with something that looks open, but in the end it's still kind of vendor locked in, a lot less than regular databases, but still kind of locked in. Thank you, everyone. Bye.